Have you ever imagined parking your car in space? It might sound like a scene straight out of a sci-fi movie, but the concept is not as far-fetched as it seems. It sounds like science fiction, but it's closer to reality than you might think. The idea of parking in space is becoming more plausible with advancements in space technology. In the vast expanse of our solar system, there exist special places called Lagrange Points. These points are not just random spots, they are carefully calculated positions where gravitational forces balance out. These points act like cosmic parking spots. Imagine being able to park a spacecraft in space and have it stay put with minimal effort. Spacecraft can park there and stay put with minimal effort. This is incredibly useful for long-term missions and space stations. Lagrange points are like gravitational sweet spots. They are areas where the gravitational pull of two large celestial bodies, such as the Earth and the Sun, create a stable equilibrium. They are locations where the gravitational forces of two large bodies, such as the Earth and the Sun, create a stable equilibrium point. This means that an object placed at a Lagrange point will remain in a fixed position relative to the two larger bodies. Imagine a cosmic tug-of-war where the forces balance perfectly. This balance allows for a stable position in space, making it an ideal spot for satellites and space stations. These special points, named after the Italian-French mathematician Joseph Louis Lagrange, offer a unique advantage for space exploration. Lagrange's work in celestial mechanics has paved the way for modern space missions. They allow spacecraft to maintain a relatively stable position with respect to the Earth and the Sun, reducing the need for constant course corrections and saving precious fuel. This efficiency is crucial for the sustainability of long-term space missions and the future of space exploration. To understand Lagrange points, we need to delve into the intricate dance of gravity. Gravity is the force that attracts any two objects with mass. The more massive the object, the stronger its gravitational pull. In our solar system, the Sun's massive gravity holds all the planets in orbit. Similarly, Earth's gravity keeps our moon in its orbit. Lagrange points arise from the interplay of these gravitational forces. Imagine Earth orbiting the Sun. At specific points in this orbital dance floor, the gravitational forces of the Sun and Earth, combined with the centripetal force of an object's motion, create a net gravitational force that's exactly counterbalanced. These points of equilibrium are the Lagrange points. There are 5 Lagrange points in the Sun-Earth system, labeled L1 through L5. These points are unique positions in space where the gravitational forces of the Earth and the Sun, combined with the orbital motion of an object, create a stable location for that object to park. Each point offers a unique vantage point and advantages for space exploration. They serve as strategic locations for various types of missions, from solar observation to deep space exploration, and even potential future space habitats. L1. Positioned between the Earth and the Sun, L1 is a prime location for solar observation. This point allows spacecraft to continuously monitor the Sun without the interference of Earth's shadow. Spacecraft parked at L1 have an uninterrupted view of our star, providing valuable data about solar flares, coronal mass ejections, and other solar phenomena. This data is crucial for understanding space weather and protecting our technology on Earth. L2. Located on the opposite side of Earth from the Sun, L2 is a gravitational sweet spot for space telescopes. This location is ideal for observing the distant universe, as it offers a stable environment far from the Sun's heat and light. Shielded from the Sun's glare, spacecraft at L2 enjoy a stable thermal environment ideal for sensitive instruments. This makes L2 a perfect spot for missions like the James Webb Space Telescope, which aims to peer into the early universe. L3. This point lies directly opposite Earth on the other side of the Sun. Although it is not currently used for any missions, it remains an intriguing location for theoretical studies and future possibilities. While L3 remains hidden from our view, it has sparked the imagination of science fiction writers as a possible location for a counter-Earth. This hypothetical planet would share Earth's orbit but remain perpetually out of sight behind the Sun. L4 and L5. These points form the apex of 2 equilateral triangles with the Earth and the Sun, located 60 degrees ahead and behind Earth in its orbit respectively. They are known as the Trojan points. Unlike the previous 3, L4 and L5 are remarkably stable, making them natural collection points for asteroids and other space debris. These points could potentially serve as future bases for asteroid mining or as way stations for missions traveling deeper into the solar system. Not all Lagrange points are created equal when it comes to stability. These unique positions in space where the gravitational forces of two large bodies like the Earth and the Moon balance the centripetal force felt by a smaller object are fascinating yet varied in their characteristics. Think of it like balancing a ball on a hill versus resting it in a valley. The difference in stability is stark and can be visualized easily with this simple analogy. L1, L2, and L3 are like the ball on the hill, inherently unstable. These points require constant vigilance and adjustments to maintain a spacecraft's position. Spacecraft at these points require occasional course corrections to stay in position. Without these adjustments, the spacecraft would drift away, much like a ball rolling down a hill. Imagine a marble perched atop a dome. Any slight nudge will send it rolling away. This is the challenge faced by missions positioned at L1, L2, and L3. In contrast, L4 and L5 are like the ball in the valley, inherently stable. These points offer a natural resting place where objects can remain with minimal intervention. Objects at these points tend to stay put with minimal effort. The stability here is akin to a ball nestled comfortably in a valley, requiring little to no energy to maintain its position. It's like a marble at the bottom of a bowl. Even if nudged, it will naturally roll back to the center. This inherent stability makes L4 and L5 ideal for long-term missions and studies. This stability makes L4 and L5 fascinating locations for studying primordial objects. Scientists can place instruments and telescopes here to observe the cosmos without the constant need for adjustments. Asteroids trapped in these points, known as Trojan asteroids, offer a glimpse into the early solar system, preserving remnants from the time of planetary formation. These ancient objects provide invaluable insights into the building blocks of our solar system, helping us understand its history and evolution. Section 5. Lagrange points in action, real-world examples. Lagrange points are not just theoretical constructs, they are actively utilized in space exploration. Spacecraft have been stationed at these points to study the Sun, observe the universe, and even monitor Earth's climate. One prominent example is the Solar and Heliospheric Observatory, or SOHO. Positioned at L1, SOHO has been continuously observing the Sun since its launch in 1995, providing crucial data about solar activity and space weather. Another example is the Wilkinson Microwave Anisotropy Probe, or WMAP. Stationed at L2, WMAP mapped the cosmic microwave background radiation, the afterglow of the Big Bang, providing insights into the early universe. These missions highlight the practical applications of Lagrange points in space exploration, offering a cost-effective and efficient way to position spacecraft for long-duration observations. Section 6. A telescope's perfect perch, the James Webb Space Telescope. Perhaps the most ambitious mission to utilize a Lagrange point is the James Webb Space Telescope, or JWST. Launched in 2021, JWST resides at L2, a million miles from Earth, where it enjoys an unobstructed view of the cosmos. JWST's infrared vision is so sensitive that it needs to be shielded from the sun's heat and light, making L2 the ideal location. From its perch at L2, JWST is poised to revolutionize our understanding of the universe, peering back in time to observe the first stars and galaxies. Section 7. Trojan asteroids, cosmic fossils at L4 and L5. While L1, L2, and L3 are unstable, L4 and L5 host a fascinating population of celestial objects, Trojan asteroids. These asteroids are trapped in these stable points, orbiting the Sun along with the Earth. Jupiter's Trojan asteroids are the most famous example. These cosmic fossils, remnants from the early solar system, hold clues to the formation of planets and the conditions that prevailed billions of years ago. Studying Trojan asteroids provides valuable insights into the history of our solar system and the processes that led to the formation of planets, including our own. Section 8. Future Frontiers, Lagrange Points and Beyond. As we venture further into space, Lagrange points hold immense potential for future missions, serving as cosmic waystations for exploration and beyond. One concept envisions using L1 as a staging point for solar-powered spacecraft, harnessing the sun's energy for propulsion. Another idea proposes establishing a lunar base at the Earth-Moon L2 point, providing a strategic location for lunar exploration and resource utilization. Furthermore, L4 and L5, with their inherent stability, could host future space colonies or space-based infrastructure such as fuel depots or communication hubs. Section 9. Conclusion. Unlocking the secrets of the cosmos. Lagrange points, once a mathematical curiosity, are now integral to space exploration. These cosmic parking spots offer a unique advantage, allowing us to position spacecraft for long-duration observations, study the sun, and unlock the secrets of the universe. As we continue to push the boundaries of space exploration, Lagrange points will undoubtedly play an increasingly important role. They are a testament to human ingenuity, allowing us to navigate the cosmos with greater efficiency and unlock the mysteries that lie beyond our home planet. If you enjoyed this journey through the cosmos, don't forget to subscribe to our channel for more explorations of the universe and its wonders.